So good morning. I have the pleasure this morning of introducing to you, but you don't know him already, Adriano Fonseca. Adriano started his career in Brazil and then has since elsewhere, including in France, doing something that was kind of a master's, but not quite a master's, depending on how you look at the French education system. And then has joined us for his PhD a couple of years ago, and he's at the stage now of very, doing a proposal defence, but much further along than is typically the case when we do proposal defences, which is good things and bad things about it. But in the meantime, the plan for today is he will talk for about 40 minutes roughly and explain context, what he's already done, why it matters, what he's planning on doing to complete his PhD. The committee are Bathymetric, of course, here, Kim Lowe, Larry, me, and Mark Roche in Belgium, who's on the line there. So, you're away.
Hello, everyone. Good morning. Thank you for coming. I'm happy to present the work that we have done so far and propose the direction that I'm taking my research. So it is called Subsampled Graph-Based Bathymetric Data Processing. Okay, I'll have to start with a disclaimer. I heard that there was some problem with the word graph throughout my text. And when I'm talking about graphs and when I'm talking about trees, I'm not talking about these two. I'm in fact talking about these. So when we talk about trees, it's a series of nodes. And in this case, this can be soundings, which is what we use in this project. But that can be any data point connected by edges and without any cycles. So something that looks kind of like this with branches. And when we're talking about graphs, we mean interconnected nodes that are connected by edges and creates this graph structure. So the bottleneck in multibeam and bathymetry data has shifted from acquisition to the processing side. So from early 2000s, when most of the methodologies were created, where we had a couple 100 million points, now it's very common to have billions of points in a single survey. But the problem is the methodology we use, I wouldn't say the problem, but the methodology we use is still the same from that time. And most of the decisions were made because of limited computation and limited technology. So why now? Why make this shift now or attempt to answer this question now? Well, the massive amounts of data we're getting, right? So multibeam data itself has become massive. So the surveys that we do are in the order of billions of points. Seabed 2030, trying to map the world's ocean. So we're trying to get as much data as we can as we speak. Not only that, but autonomous vehicles, right? Dual Drix was a project that we ran over a very big area of the ocean using two autonomous vehicles. Sail drone, Voxometer, a sonar that just came out recently by Artisonic. I don't mean to make any advertising for any companies, but the idea of this is they were putting 10 swats out at a time per ping. So it's massive amounts of data. They were actually having trouble dealing with some of this data. Not only that, but there's been a significant increase in the community's interest in AI and machine learning and these kinds of methodologies. This just from the last CHC, these are all the papers that were somewhat related to either deep learning or classic machine learning or any kind of learning algorithms in general. So it's a big community push towards this. We ourselves have started a machine learning working group, and I'm very happy that Maso is also aligned with us. He's a very big part of the creation of this group, where we are attempting to bring everyone that's working on these sorts of problems together so we can create our benchmarks, our metrics, our data sets, etc. And we can discuss how the community is going to take in these different types of algorithms. Also, many industry partners are interested, and many hydrographic services are interested. So UKHO, NOAA, SHAM have all made big initiatives to move towards machine learning and AI processes. Before we start about the contribution, I want to say that one of the biggest things that I will try to address in this proposal, and I'm trying to address in my study, is the use of grids. So Historically, sorry to say historically, traditionally, a lot of this processing has been done in grids. So a lot of the way we do it is we create a 2D grid of the soundings or of the survey that we're working in, and within that grid, we do some kind of consolidation. For example, median, UKHO likes to use show bias, etc. And within that smaller subset of the points, we do all our processing, or we create our processing, then we create our services from that. The problem with grids is they create structure in the data inherently. You're fixing a resolution throughout your survey, and with this fixed resolution, it's mostly wrong. It's most of the time it is wrong, except for a few parts that it is right. This is a design choice in most of an implementation choice in most of these algorithms. It's not a design necessity, but it was a necessity for the computational power that we had at the time. So these are the contributions to my paper. I would like to start with Bathy Subsample, which is going to be a conservative, anomaly-aware subsampling algorithm. And the idea is, how can we still have the benefits of the grid, which is the reduction of the amount of data points that we have, but at the same time limit the amount of artifacts and the amount of structure that we add to the data. So this idea came where we work with the points as a point cloud, and we consolidate them in an intelligent way that I'll explain further on. And we're able to have a subsampled point cloud that we're able to work with and make our problem tractable. The next part is going to be a graph neural network framework for learning on this data. So once we have the subsampled point cloud, how do we decide what is bathymetry and what is not bathymetry, right? How do we put this into that workflow and pipeline that we're used to so we can create those services? And finally, we need to compare all of this, right? And this is in two parts. Is the Bathy Subsample algorithm worth it? Is it worth all the extra computation? Where we can just use a regular median grid or a voxel grid, or use something like Huber chart, and which has been optimized for many decades, and we can use it for a couple of decades, sorry. and will be more computationally viable than the algorithm I'm proposing. And then at the end, is the product that we have coming from the network good enough or better also to make it worth it? So part one, background. I want to go over some of the traditional methods, right? Ones that you're very aware of are, for example, cube and chart, right? The idea of cube and chart is you create nodes, usually evenly spaced, around your survey, and within each of those nodes, you look at their neighborhood, and you propagate the depth and the uncertainty of all the points within that neighborhood, and you try to estimate what you believe in that node the depth and the uncertainty is. And with cube, that is again by choice, not by necessity of the design. This is done with an even grid, and the nodes are the corners of each of those grids, or the centers of each of those grids. No, it was corner, that's right. And then there's chart, which was an expansion to this work, where you have a variable resolution, right? So you can break that space into smaller spaces where the data is more dense, and you can do the exact same process. Again, the regular grid is commonly applied, but it's not a constraint. It was more of a computer resource constraint. There's also methods that, such as charm, that estimate surfaces on top of the sounds. So you create sub areas. You can use an octree, for example, similar to how the hierarchical part of chart is made to create smaller areas based on your sounding density, and you try to estimate surfaces with them. The problem with these designs, in my opinion, is that they rely on the soundings too much. So they rely on the specific sounding to create that grid. And as we know, soundings by themselves are inherently noisy, right? Inherently have a certain certainty. And I believe an approach similar to Cube is the more correct way, where we try to estimate a sounding based on the soundings that we have around it and uncertainties that we have around it. And manual editing remains the dominant cost, right? A lot of manual editing is still done. Many hydrographic services do most of their pipeline manually. Not only that, but a human in the loop is always going to be necessary when we're talking about safety of navigation. Someone is always going to have to take a look and do a quality assessment of what's being done. So if we can push that back as much as possible, and we can make their work as easy as possible, I think that is the way that we try to automate that process. And another problem with manual editing is a work by Shum recently showed that they had hydrographers agree about 30% between all of them. So it's a very subjective way of doing the processing as well. So here are some of the literature solutions to that apply machine learning to some of the problems that we identified. One of them is the work that Shum and UKHO just recently proposed, which works with SWATs specifically. So they have a UNet network, just a CNN UNet, and they attempt to go through the SWATs and identify noisy points or points that do not comprise the seafloor that they're looking at. There's also work by UKHO, which when I first started this research, this was actually the most novel one. So it's the one I based myself a lot on when I first began. But the problem with this one is it creates voxel grids of the data, right? Voxel grids of the data, voxels being 3D pixels, has the advantage of being able to have different values of depth per XY, unlike a 2D gridded surface. But at the same time, it also adds a lot of structure and artifacts to the data, right? As you can see here. Not only that, but it creates a lot of sparsity, right? When you are required to create a grid that goes up to a certain depth, down to a certain depth, you create a lot of sparse voxels that don't have any soundings in them. Not only that, but if you want to keep it computationally tractable, you need to move how far you're looking as you go along the survey. If you're at a survey that goes from 10 meters to 200 meters or even further, that area starts getting big unless you control it on its way. There's also point cloud native solutions that have become more mature for processing point clouds in the point cloud domain, or in a graph domain. These are, for example, PointNet++. I just want to make a note that PointNet++ was not made by the creators of PointNet. So I think that's a very nice way to create enemies in the literature when you call your revolutionized PointNet. But anyways, the idea is they work directly on the graph. So they subsample and group the point cloud and directly on them classify and segment. The same for DGCNN, Dynamic Graph CNN for learning on point clouds. The idea is you attempt to turn the CNN, or the convolutional neural network layer, into something that can be used on graphs. So it's called an edge convolution. So it turns the pixel-wise convolution into an edge of graph convolution. And that way you can do something akin to a graph neural network. Finally, I just want to make a note that data sets are not yet at a level playing field for machine learning. There's no processing independent ground truth. What does that mean? All the ground truth that we have is not from someone draining the ocean, going down there and measuring what it should be. So it's not a real ground truth. All the ground truth comes either from a certain process, such as cube or chart. So inherently, I'm not saying it's wrong, but inherently it has assumptions and biases from those algorithms. Or it's done by a hydrographer, by hand. And that hand annotation, again, comes with biases and comes from decisions made by the hydrographer. There are also many formats and scales. And this a lot has to do with how most of the software that we use is done, right? Every software has their own specific format, has their own specific way of handling and processing the data. So what are the implications for this, right? We need to create reference surfaces to create data sets for machine learning that are that have their decisions reported alongside. So for example, if something is hand annotated, the surveyor has to have gone and written down all the decisions they made. Or if you use a specific software, how were all your decisions for that software made in a way that we can replicate, right? We can use targets of known geometry, which comes back to if we have measurement, we're able to compare. Or a consensus surface, which is something that in the machine learning working group we're talking about. So we have a couple of surveys that we decide, and then based on a consensus among our peers in the working group, we decide, okay, this is what we believe truth is. So now I want to talk about the structural problems that motivated the point cloud native pipeline, right? So this is the first gap in this work, which is the representation-induced structure food. Right? So I talked about how grading produces artifacts, and for example, in slopes, which is the biggest problem with gridding, we're never able to correctly represent and create these staircases, right, of the slope. Not only that, but the areas that we're most interested in for safety of navigation or for difficulty in classifying are the areas where grading hurts the most, right? So high relief terrains, very sharp transitions, anisotropic sampling. What does that mean? Like areas that are more dense together with areas that are less dense, which, as we know, is inherent to a multibeam survey. And I just want to say that the case is not against gridding. I'm not saying gridding is bad. I'm saying gridding has limitations. And if we can find a way that works on those limitations, and maybe if we don't have the processing power for it right now, it's a technology that we can show that in the long run will be better than gridding. That's what I'm trying to do here. Gap 2, which I alluded to, the sparse and heterogeneous sampling. Everyone has a trouble with that word. Gabby, this one's for you. It's inherent to surveys, right? This can be either from a beam fan geometry. It's always going to be, or not always, but it's usually more dense in nadir and less dense in the outer beams. If you have overlap during your survey, those overlap areas are going to be more dense, even if you have 200% because of the beam fan geometry. And how you run your lines too. If you run them parallel, if you run cross lines, you're going to cause different densities. So it's not something we can control, and it's not something we should try to control. And at the end, you have surveys that look like this, with varying levels of density depending on the terrain relief, depending on acquisition, right? So an effective scale needs to be local. It needs to be in areas that are less dense. You know, that have a lot higher scale, for example, or if we depend on structures on the seafloor, and areas that are less dense can be of a smaller resolution, which makes the case for point cloud native. This point cloud native doesn't care about that. The points are where they are, and that's how we process them. And gap 3, scale, redundancy, and computational tracking. At the end of the day, this needs to be a software that people can use. If we plan to put this in a pipeline for hydrographers to use, it needs to be able to run on the computer. They shouldn't have to access a supercomputer to be able to run this. So it's something that we'll keep in mind throughout the project, or throughout my proposal, is can this be computationally done? Full disclosure, I don't believe by the end of my PhD we will have something that could be run in real time for hydrographers to use. But it is something that I can show that can be done once the technology catches up to you, or once the optimizations catch up to it, right? The other methods have had a 20-year running start, or head start. So here's a proposed direction, right? A point cloud native pipeline in 2 stages. The first stage, where we subsample that point cloud. And one note that I'm going to make is the idea of this subsampling is a little counterintuitive. We're not trying to justify keeping points we're trying to justify removing them. So here's what we worried about with safety of navigation, right? We want to keep those anomaly points. We don't want to remove them. We don't want to remove the weird points, because the weird points can be either noise, and most of the time it is noise, or it can be hazards. So we don't want the subsampling stage to make any decisions regarding what is bathymetry and what is not bathymetry. What we wanted to do instead is consolidate redundant data. So on flat seafloors, for example, where we have the same depth throughout, we can consolidate it into a statistically proven or a statistically aware consolidation of that sounding. And a comparison study, right? At the end of the day, we need to compare it with, we need to show people that you should use this, it's worth using this, right? And in between those two, we have the graph neural network that's going to make the decision of this is bathymetry, this is not bathymetry, this is what we should use for the final products. So, research topic 1, the Bathy Subsample algorithm. The Bathy Subsample algorithm has already been implemented, and we actually have a paper submitted on it. We're just waiting for the people at Jere A. And the idea behind it, as I said, is it's a conservative feature retention. We want to conserve every point that we have doubts about and consolidate every point that we're sure are redundant. Right? So this is where the mode preservation. Oh, sorry, I'm pointing here, Mark. I don't know if you see it. The mode preservation part of it is we want to preserve modes that are redundant or with areas that are very correlated. We want it to be uncertainty aware, right? So if we're farther on the beam or if we're in an area of very rough terrain, we want to be able to adapt our scale as well. And we want it to be compatible downstream, right? So for example, with the graph neural network that comes after, we want to be able to output this in a format that can be turned into a graph or that can be consolidated in some way. So here's the pipeline. We take the raw point cloud, we partition it to be more computationally feasible and also to be able to parallelize it. And this partition is done through Morton ordering or Morton code, which is just there's different ways you can look through a raster or you can look through a point cloud, and the Morton one tries to guarantee that points that have similar codes are closed spatially. That's the idea. We want to keep points close. We want to keep points in the leaf close.
Adriano, I'm just going to stop. You said points that have similar codes.
Codes, yes.
CODES.
Yeah.
Does that mean value?
That means the code that is given by the Norton coding. So the Norton
representation of depth.
It's a representation of XYZ. So it's like a hashing of their XYZ position. And points that have that similar hash code are closed in space.
Okay. Some of us, words like that are coded. We have no idea what they mean.
Yeah, that's what I mean.
Thank you.
And then we went to the consolidation. So within each of these leaves, we separated into voxels. Unfortunately, the voxel is still used here. There's still some structure, but it's not the same because the voxel is not actually going to force that resolution. It's actually just a limited on the neighborhood that we're looking at. And within that neighborhood, we're going to find up to n. In our case, we use 3 hypotheses or modes within that voxel. And we will keep those along with their strength. Our strength being how many points were used to create that mode. And finally, we'll have the reduced point cloud with weights for every point. This is the original point cloud. This would be what that subsampled point cloud looks like, where red are the anomaly points, and you can see parts that are spurious or like edge effects tend to be anomalous in this case, and areas that are very redundant tend to be consolidated into the modes and the medians. And that comes down again to the TVU-aware mode consolidation, right? The spikes may be wrecks, they may be fish, they may be hazards to navigation. So we can't get rid of them, right? They could be true measurements. So instead, what we do is we create these modes, as you can see here. So this would be the depth distribution across one of those voxels inside a leaf. So we fit modes to it. Over here, the algorithm is fitting 2 modes. And every point that's within, for example, 3 standard deviations, we keep. and it will be consolidated into this mode. Every other point is left by itself with a weight of 1, for example. So this is the important thing, right? Flag points, or points that are anomaly, are passed through unchanged. You don't touch them. The system tries to justify the removal of points. We have to show that the point is worth being removed. What does that mean? It is within 3 standard deviations of a mode found by the GFM algorithm. We're justifying removing the point, not keeping it. And these are some of our primary results. We got reduction ratios of up to 90% on shallow water EM2040 data. And we were able to show that even when we reconstructed the surface from those 10% of points, it was valid and it was within specs. The multimodal structure was preserved. So here I have examples of actually slope data. As you can see, the depth is more evenly distributed across the depth range. And you can see that we were able to pick up multiple modes or multiple depth hypotheses within the area, whereas regular algorithms, for example, would use median for this, tend to fall either between different modes, or in the case where the depth is fairly constant, fall directly on the main mode. Median is a very, very good estimator, but it's a very, very good estimator when we have one mode, when it's flat. If we have multimodal distributions, the median is actually very poor. And random sampling as well. I'm not going to make it a case for random sampling. It's bad. So this takes us to the research topic 2, right? Now we have the subsampled data and we have kept all the anomalies. How do we decide what is bathymetry and what is not bathymetry? This is the Graven network, graph bathymetry network. And this is how it works. It's essentially an autoencoder network. I realize I should have been more here. Oh, thanks for adjusting the camera.
Yeah, it's adjusted.
Yeah. It's an autoencoder network. What does autoencoder network mean? You have an input, you encode it into what we call a latent space, which is just a compressed version of your data. And then we decode it, we decompress it back into what we believe the input was. And we train the network on that. So we try to make our input and our output as close to each other as possible. And close mean a low reconstruction loss. We have an extra step here, which is this is a variational autoencoder. The variational autoencoder, instead of trying to encode the data into a compression, it actually encodes the data into a mean and a standard deviation of what we believe the distribution of that compression should be. And the advantage of this is we can then sample from this latent space, sample from this average and standard deviation, and decode the different samples that we take. And this has 2 advantages. The first advantage is it makes the score smooth across, so it makes the reconstruction loss smooth across classes. If for example, we didn't care about that and we were just using a regular autoencoder, points that are very similar or in similar surroundings could have wildly different scores or could have wildly different latent spaces. That way we keep everything tight and together and we can create a smooth transition between scores, between less right and more right. This is kind of what that would look like, right? So we have here on the x-axis the log of reconstruction loss and the PDF of those. And we can see that points that have very high reconstruction loss, so points that our network was not able to decode, are points that were not bathymetry, and this is validated through hand-annotated data. And points that have low reconstruction loss are bathymetry. And one thing I forgot to mention is what makes this possible is we train the network on clean data. Essentially, it learns what clean data should look like. It learns what bathymetry should look like, and in a sense overfits it to only knowing how to reconstruct clean bathymetry properly. And when we add noise to that system, or when you add points that are not bathymetry, it has a hard time reconstructing this and gives a high reconstruction loss. And so The advantages of this are the anomalous point reconstruct poorly, and we're able to see those anomalous points because they have a high reconstruction loss. And it doesn't require label examples. It requires clean examples. So they still have to be clean, but it's just one class. It's clean. So why graphs, right? I talked about all the problems with gridding, but when this graph comes in. So soundings by nature are unordered, irregular, and locally structured, right? With different densities throughout. And graphs are actually very good at representing that, right? Graphs only care about the edges between nodes. If we treat every sounding as a node, we only care about the edges, and the edges will give that distance. The edges will give that relationship between the points. Message parsing, which is inherent to graph neural networks, actually aggregates neighborhood information without imposing a grid. So if we define that neighborhood through some sort of triangulation or fully connected graph, etc., if we define that neighborhood, we're able to aggregate the information of all its neighbors inherently in the way that the graph neural network is designed. And we can construct patches of arbitrary scale, right? If we define the number of neighbors that we're worried about, and areas that are less dense, that area is going to be bigger. And in areas that are more dense, that area is going to be tighter. The way we do this is we do, in our algorithm, we do a Delaunay triangulation. So this is what that graph will look like at the end, where every point is that subsampled sounding. And we do something like this, where we have in the immediate neighborhood, we keep a very dense cluster of neighbors, and we take less and less neighbors as we go farther along. And the idea of this is Tobler's first law of geography, right? Everything is related, but things that are closer are more related. I don't know if I misquoted. I misquoted that, but I think the idea gets across. So these are some of our preliminary results, right? I've shown you the log reconstruction loss. It's fairly smooth with two very obvious supermodes. You can see tiny little modes within them, but two big supermodes. So this proof of concept was important because both we were able to show that it works. It's maybe not in its most optimized or best way, but it works and it converges, which were the two things that we were worried about. And it converges within an acceptable amount of time. It only takes a couple of hours to train and not months on a supercomputer. So this is very good. But the remaining gap is, at the end of the day, we want surfaces, right? At the end of the day, we want, at least now, the way that it's done, we want a surface at the end. So how can we reconstruct the surface from these points? And that's where the decoder improvements are going to come in. Well, before showing the decoder improvement, I'm just going to show quick examples of those losses and how they can be validated with your eyes and by looking at the survey. So, for example, we have loss of bottom sections, where those points that have a high loss, those points that constitute that loss of boundary detection actually have a very high loss, and we're able to identify and clean them out with a simple threshold. Deep artifacts, for example, shallow boulders and borders, areas of very rough terrain, very noisy data, and these are shallow artifacts. And the cool thing about this is we're able to show that the network's also not biased to what noise should be. It's not saying that shoal points are noise. It's not saying that deep points are. It's not biased by depth itself. So this is what we propose for the decoder, because that's not been done yet. It's a folding net style surface decoder. And the idea is the decoder starts out with a sheet. You can think of a sheet with nodes across it. So you can pick it up from one of the nodes and bend that sheet. And with each pass through each of the layers, it attempts to fold that sheet into a good surface reconstruction, good in the root mean squared or whatever sense that you're looking at. And the advantage of this is the output is a parametric patch. So we just have a patch that tries to describe that leaf in the best sense, weighing obviously less anomalous points more than high anomalous points, right? When we're pulling that surface, and we have an output that is a surface. And then how do these two fit together, right? I've talked about this, I've alluded to this, and the idea is we want to make the training of the graph neural network more tractable and more doable, something that we can run in a day, a couple hours instead of months. So we need to subsample that point cloud in an intelligent way, or at least in a way that is applicable to bathymetry, and it's something that we've thought of for this specific application and not something off the shelf. That's downsampled point cloud is then triangulated or created. We create a graph from it. We connect those points. This can be through Delaunay triangulation, for example, or it can just be fully connected. And then we go through the network and we classify and we give our terrain predictions. The output is going to be a surface with uncertainties on each of those nodes of the surface. And then finally, research topic 3. The research topic 3 is going to be the ground truth question, or how do we compare these algorithms, and how do we compare, even within my algorithm, how do I say that it works better, works worse, it's working fine, is worth it, or has a direction for optimization, right? So, as I've alluded to before, no processing independent reference exists, right? So cube and chart are widely used for this, but they encode their own assumptions into the data, right? So yeah, I'm not saying these assumptions are wrong or right, but they are not neutral, right? So some of the candidate references that we've discussed in the machine learning working group is, for example, using targets of known dimensions, right? So this would be pipeline independent. It's just what the things, what the size of the things are. So if we're able to identify targets that we know the exact size of, we're able to calibrate or test our system. A consensus-based from multiple experienced operators, or a consensus-based approach. The problem with this consensus-based approach is the consensus part. As we saw, as the study showed, only about 30% agree. And that's between people of the same service that probably process things in a similar way and maybe go out for coffee together. And refining the choice itself is a contribution. So I hope to have this by the end of my PhD, because I think it's a very good contribution. And I think it will pave the way for other processes as well to come. So, 3 input regime, 1 pipeline, right? So I want to test my network for full resolution of samples to see if the subsampling that I'm doing is affecting that output in any way. I know for a fact that subsampling is going to be less efficient and it's going to take a really long no subsampling, full resolution is going to take a long time to train, but I want to show that the compromises that we're making with the subsampling are worth it at the end. I'm going to try with my subsampled point cloud and test it as well with the cube chart filter data to compare it to traditional methods. And the evaluation, this is also something that is an active area of discussion, and an active area of discussion for the machine learning working group is how do we validate these machine learning models in a way that makes sense to hydrography, right? We're still going to use F1, accuracy, precision, that machine learning language, but we want to translate this into a hydrography language, right? Not so hydrographers can understand it, no, but yes, also, but so we can see the physical implications of our decisions, right? So, for example, a kind of surface fidelity where we just do a reconstruction loss and see how well we're reconstruction based on the baselines. Future recoveries, this is more of a target detection sort of metric. Uncertainty calibration, make sure that the uncertainty that our algorithm is giving is explainable. For example, if you're saying, oh, you're super precise here and the uncertainty is 1 centimeter, but the inherent uncertainty of your data is about 10 to 20 centimeters. Something's wrong there. Intractability, right? We want to be able to test these in a way, in a controlled environment to show, oh, this algorithm takes this much to run, this algorithm takes this much to run. This is how they compare it and how they classify, etc. So what's being done about it? Well, right now we have a unified data set that we're working on at the Machine Learning Working Group, where we have different areas. There's actually there's data from NOAA, data from Sean, data from Bedrock themselves, and anyone can have access to this. If you want it, please let me know and I'll give it to you. And we have our GitHub, where hopefully we'll get a little more activity, but the idea is to discuss all those metrics, discuss all the work that we've been doing. So that's it for the work. Now I want to talk a little bit about the timeline. So hopefully, I'm defending the proposal now. Hopefully it'll be accepted. But the idea is we'll keep revising that paper. And we actually have another paper underway where we expanded how the subsampling is done to include different features and not just the XYZ coordinates. So we developed some graph features that actually aid in defining anomaly for that subsampling area. And that's going to be another paper that's coming out. We'll transition to the Graben full implementation by August and have that finalized. Hopefully with a data set as well. And we've been talking to Maso and talking to the machine learning working group about having actually publications based on this, publications based on the data sets and the metrics, because those are a contribution themselves. Have the manuscript submitted in January, start the comparison suite, and have everything done by April where I finalize my manuscript, and hopefully see you all here in June. All right, same place, same time. Oh, maybe a little later. So here's some of my contributions, right? I want a coherent, standards-aware pipeline for bathymetric surface reconstruction that makes representation choices explicit, quantifies trade-off, and supports hydrographic validation practice. I have an idea of what I think is the best processing pipeline, but I want to show why. I want to show the trade-offs. I don't think it's the best because it's perfect in every way, but I think it's the best because some of the trade-offs are worth it. And I want to show this with these 3 steps, right? The subsampling algorithm, the network classifier, and the comparative study. And this is what I want you to take away from this. I want you to have these in mind if you want to think about the work done. What constitutes an informed data representation choice? So that's something I'm going to be thinking about, right? Why am I choosing graph? Was it a mistake to choose graph? Should I just stick to grids? This is what I'm going to try to prove. Can ML-centered designs catch up to and eventually surpass established algorithms? As I said, I don't plan to buy my, well, I'm going to plan for it, but I don't suspect it will happen, that I will have an algorithm that is as optimized and ready to be out into the world and to be used by a service in their pipeline. But I want to show that it can get there, either through technology or through optimization. And how can we adapt decades of knowledge in hydrography into this ML world, right? A lot of the work that's been done has been picking up ML and deep learning techniques off the shelf, but how can we use hydrography knowledge to actually improve this? That's also something I'm going to be focused on. And that's it. And I provided a comment on a lot of
Thank you, Adriano. There are a wide variety of topics there, and it's hard to be an expert in all of them. So I'm sure we all have a lot of questions about one part of it, maybe not so much about the other part that we know more about. It's hard to get the whole thing put together. All right, so we have a little time for questions, and we're happy to take questions from the audience directly. Lots of questions. All right, let's start with Christos.
I'd like to ask you, in defining the neighborhood, what is your cutoff? When do you decide that this is enough? I have the distance I search is enough. And how do you deal when you have gaps in the data? When you build this the long triangulation, you have gaps. How do you deal with it?
In which part, the subsampling part or the graph, the network? In both of them, I define a certain neighborhood. But I'll say both then. Yeah. With the graph, unfortunately, right now is user defined. So you define what you believe in meters a good neighborhood would be. And the
sorry for that. Based on the survey.
Based on the survey. Yeah. Based on it's defined for each survey. That part, because that part is not learned. It is learned, but within a specific survey. So it just learns it as it runs. For the graph neural network, we actually we have those 3 neighborhoods that are also defined based on density of the survey, and they're normalized. So even if in areas, at least for training the network, in areas that are more dense or less dense, the graph looks about the same. It just depends on the number of neighbors around it, but it's defined based on the density of the area that you're looking at.
Okay, Brian, I don't know.
You put together a very nice proposal and made it well, so congratulations for that. To your second question there, can these ML-centered designs catch up and surpass established algorithms? So with the established algorithms, you mean nothing's ever done, but it's, they get refined at different. At some point, they're good enough. They're sort of, okay, we're leaving this alone. This is solve a problem.
Yeah.
With ML, it's less clear to me, or maybe because I'm not an ML expert. Well, how you determine that good enough, and a related, so that's one sort of question related to that, I think, is be quantified or give you an idea or a way to estimate how much data you might need to collect, because these models are, as we know, very data hungry. So is it, how close is it to, well, if we give it a map of the entire world's ocean, we can train this. So, okay, great, but then you've mapped the world's ocean, so like, how useful is that?
Yeah.
So
What I mean by catch up, I do think the machine learning, in a perfect sense, where we have enough data, it definitely can catch up, and it could possibly do better, probably do better. What I mean by catch up is mostly in the technological and running sense, right? And a product that can actually be used by hydrographers. And I don't, unfortunately, I don't have an estimate of how much data that would be. And I think we decide when it's done when it follows or it falls within the specs that are required by hydrographic services. And I think, at least as a first step, that's what we can aim for, is be good enough to be put into a pipeline, and then improve it enough to show that, well, actually the service requirements are actually very lenient. And they are very lenient, and they're very conservative. And it's like, well, we can do better than that, but first we need to show that we can deliver what they want, and then we can talk about being better. Does that make sense?
Yeah. You've got a comment and a question from online. Yeah, he says, great job, really interesting work. Recommend starting writing the thesis now, says next spring.
We've had that conversation before, Gary.
Elias says, Adriano, my question is, how much retraining or fine-tuning is required for your VAE to generalize to data sets that were not included in the original training set?
Okay, yeah, that is another thing. So the generalization problem. The best way, or I would say the easiest way to do this would be separating different sorts of bathymetry, right? And make almost like a classification problem out of it as well. So we have a model that's very good for shallow water in the North Atlantic. We have a model that's very good for Alaskan. We have different submodels that work better in those areas. They share the same initial layers, and those layers can be trained together. But then they have layers at the end that specialize to that different areas. That I think is, in my opinion, the most feasible way to do this. It's very hard to have a model that's going to generalize to all of this, again, and be optimizable and have enough data to actually provide that. So that's what I think.
Okay, any other questions? Or 22 if you prefer. We will have time ourselves as well. If you want to ask questions public too, please do. Just go ahead.
Just because I apologize, this is great. I'm really excited about this. You talk about feeling old. I've spent 30, probably 40 years trying to figure out how to densify it.
Well, for people who are unclear, the reason Adriano was hedging so much is because he didn't want me to feel old when he said this is traditionally a silly.
And if Brian feels old, I feel even older. But we spent our entire careers trying to take sparse data and make something of it. And that part of the grid, you talk about a grid from a statistical perspective, but it was also an attempt, once the data got dense enough, to give us an interpretive surface, something that we can visualize. But I'm fully thrilled about this concept of getting rid of the grids and going back to the data itself. And this is kind of a twist on what Christos was asking, but if I go out and do a standard multibeam survey, I'm on the Nautilus, and I do a deep water survey or take the tricks out and do a survey wherever, is by definition the fact that I've collected multibeam data a dense enough data set for you to be able to jump into a world of subsampling? Or are there thresholds? Do we have to make some decisions about, well, or ask another way, can we apply the same approach on every point without the subsampling set if we're on the other side of that threshold?
I think the subsampling part, or at least the statistical consolidation part, is always necessary. And this might be the Calder school of thought, but I think you have more value in that estimate than in the soundings themselves. So in a way, yes, I think the subsampling or the statistical validation or consolidation is always necessary, but there's definitely a minimum amount of points that are required to be able to do a statistical validation. So yeah, that's where that could come in. It's not, so right now it's fixed.
All right, I can see the elegance of saying that, yeah, we have some statistical redundancy here, so we'll reduce the number of points. But if the points are minimal to begin with,
well, the way we do it now,
the effort of going through that process.
yeah, the way we do it now is if there's not enough points, we just keep them all.
Yeah. Okay. All right. Well, that helps me. Okay. So you don't say I've got to reduce.
No. Yeah. Again, we have to prove that it's reductible. So we only reduce if we can show that there's a case for reducing it.
Okay.
Everything else is kept.
But is it true to say that process is really about the computational cost of training? It's really just to limit the computational costs.
Yeah, and reduce correlation.
No, and I understand that part, but I'm just wondering, is there a threshold there where we say, well, we don't have to do this at all? We just can.
Can you talk about bigger computer then?
Yeah, and that is one of my other questions. Is, at some point,
Can you give me a 4 or did I?
Yeah, maybe that will be the answer in 5 years, 10 years.
Yeah.
If I can keep going, so then I can.
Basic.
So let me kind of explain.
It's pretty. We all have more time for the rest of the committee to ask questions if they want to. Large as time constraint, yes, please. So. So also a question about the width of the modes you select and how you make that choice. How many standard deviations defines a mode?
Oh, okay.
How do you
That is a learned model. So the way it works is by estimation optimization is like a sort of optimization algorithm. You start off with just randomly generated mean standard deviation, and the model actually learns what that bandwidth, what that width should be based on the data you have. So you don't define that. The 3 standard deviations, that's ad hoc in a way. That's what it's.
But you gotta be careful because these little ad hocs.
Yeah, but that's the classical way of doing it because that's a 99% confidence interval. But we've also done it with TVU aware as well. And actually in the paper it was TVU aware where I chose 2 or 3 TVUs and that would be the cutoff.
Okay, so and that's really what I was driving to.
Yeah.
To be driven by that. And the last one, can you go to slide 29?
Yeah.
Because here for me was the magic. And you there you go. Okay. You presented this and you have a little yellow thing that says encoder.
Yeah.
I don't really, but that's magic. It says encoder and then decoder. But I get the general concept. What I don't know is what is it about the graph that's being captured in the encoder. It's got to be something that simplifies quite a bit, or it just wouldn't be worthwhile. What is it? Is it higher order statistics? What is it about the graph being captured in the encoder that's then used to create the latent space and then decode?
That is a difficult question. and sort of question that people in deep learning try to avoid as much as possible because that's kind of a black box. So what we can do is we can help it with features in some way. For example, I create the nodes and the edge features, and that edge feature would be like the distance between the points or the weights that the subsampling algorithm had. I generated roughness and other features that I can manually tell the network. But at the end of the day, the network is optimizing and encoding those features however it learns to do it. So I actually do. We can sometimes probe in there and take a look.
I'm very happy with that answer because I don't feel so bad that I don't.
Yeah, but they're high order.
It's fair. It is high order. Okay.
And the idea is you start on the first networks. You usually have very broad features. So for example, you have like a slope or mean depth, or then you go into the higher order statistics at the end of the encoder, where that would be like roughness in some areas or like Fourier spectrum of some sort.
Yeah, and so this then leads me to having that be magic. It was really magic when you suddenly show this beautiful distinction between bathymetry and not bathymetry.
Yeah.
And then you finally threw it. Oh yeah. I was about to say we trained it. This is based on a trained data set, and so.
And it's also important to say that this is a test data set. It was trained on clean data, but it was tested on a different area.
Yeah. Okay. Yeah. But it's trained on clean.
But it's trained on clean.
Yeah. You leave that one up. is trained on clean data. And I guess your answer to the first question kind of would probably be the same here too, because the question to me is, what were the characteristics of the clean data in the training set that helps it distinguish clean data from non-bathymetric?
Just not having non-bathymetry in it. It's not that it's distinguishing. The network isn't distinguishing the anomalies. It's just trying to reconstruct it as any other bathymetry.
Well,
But then
you said this is good bathymetry. Here's clean bathymetry. It's gone through the magic encoder decoder.
Yeah.
And you're looking at how well you can reconstruct that.
Yeah.
And it comes up with its optimal model to reconstruct it.
Yeah.
So it really comes back to the same question. What are the characteristics
Yeah.
of the encoding decoding process that it's using to test all the bathymetry, all the data as to whether it's bathymetry or not?
Yeah. I think I understand your question. So the idea of it is not that it's learning to, oh, when it's bathymetry, throw this. When it's not bathymetry, throw this. It's not a regression and it's not a classification. What it's actually doing is it learns what bathymetry should look like, right? So, oh, this point here is a bathymetric point, which means the points around this should look like about this, should have this kind of roughness, should be sloped a certain way, etc. And it reconstructs it. And if it is bathymetry, it's like, right, you reconstructed it correctly because it was bathymetry and that's what it should look like. But if it's trying to do that same thing to a noisy point up here, it's going to run through that same algorithm and then it's going to reconstruct it and the point's going to be here because it's trying to make it bathymetry and it's not. And that reconstruction loss is going to be very high.
Right.
And that's where this comes
No,
in.
but
the actual
you explained that
features.
one really well.
Okay, but the actual feature that it's learning, I don't know.
Yeah, that's yeah. So it is kind of magical in a sense. In terms of it's.
Any sufficiently advanced technology is indistinguishable from magic.
There you go. Okay. All right. So but this also says, and you alluded to it, that we can never expect a general model that'll work everywhere.
It could happen, but we can't expect it.
It could. And that you talked about, and I totally agree. John too. Regional models. So say this is what a Arctic glaciated environment should look like, and this is what an abyssal plain should look like. But I think it's more than regional. There's also kind of regimes. There may be ports and harbors that places where you'd expect wrecks and objects and debris and things like that. So I think that'll be a very interesting thing to see how far it can be pushed, and then what kind of distributions. And my last one is about the ground truth, which I think is very exciting and very different about you, that you're willing to try this, because many of the folks in this world just say, "Oh yeah, this is great. Look how bad that tests for me, whatever."
Yeah.
But is it conceivable that you can use something that we have a better control over the ground truth as an analog and see if the processing pipeline is appropriate? Something like a airborne, not bathymetric, but terrestrial LiDAR.
Or like a sensor fusion kind of.
Well, you can take terrestrial LiDAR. You can check it against photogrammetry and things like that. Where the LiDAR itself has enough kind of noise and uncertainties, even terrestrial LiDAR uncertainties. Yeah, that many of your approaches may be very valid in the processing stream, but at the end of the day, we can also get photogrammetry that will at least maybe not give us the absolute height. It should give us the absolute height with ground truth there, but at least give us a very, very good idea of what the topography really is.
Yeah. Oh yeah. Well, more data is always better for the validation.
Well, I'm saying that this is one that, in a sense, has fewer variables.
But you're saying run the algorithms on topography.
Yeah. Take some airborne, LiDAR data, use that as the input. In a place where there's a beautiful shuttle, whatever the shuttle data set is, that's all photogrammetry.
SRTM.
SRTM.
You could always fly your own drone as well.
Or fly our own drone. Yeah, whatever.
Yeah, no, I do.
Do it over, and if you really want to have some values, do it over a place where you know there's a USGS benchmark or something, or.
For my application specifically, yes, that actually would be nice because the structure should be very similar.
Yeah.
But that might not be the case with every different model where they can be validated that way.
Oh,
But for me,
totally
yes.
agree. Well, yeah, think about your thesis first.
Yeah, for my thesis,
What
yes.
about everybody else?
My thesis, yes, something like that would be very helpful. It's a measurable ground truth. Yeah.
The difficulty with that, of course, is that LiDAR only penetrates down to, we're talking about what it goes to. So if you're trying to combine, I've talked to Glenn Rice about it, said,
Well, I'm not talking about bathymetry at all, I'm talking terrestrial.
oh, terrestrial.
Terrestrial.
Okay, so you take the terrestrial and then sort of implicitly say, we're now.
No, forget about bathymetry, we're just talking about the algorithm.
Yeah, okay.
Yeah, and the processing pipeline. You have a LiDAR data set, and you have an SRTM data set that's ground truth.
Yeah, okay.
Yeah.
Or as
So
Ryan
when
said,
the committee starts arguing with each other, we know we've got to final. Actually, my concern with that would be that the uncertainties and the errors you get in the data are dramatically different for terrestrial than would be symmetry. So it may tell us something, but does it tell us something?
but I think
it's an interesting question.
I think in the subsampling aspect, it would be very analogous.
Yes.
You're right. The sources of uncertainty are going to be different. But I think the subcerting and the graph, the D-band or whatever, that component too, I think those would all be quite analogous. And now you'd have something again, does it really, does it look like the Rocky Mountains when I'm done?
Yeah.
But not just look like it. There are many tests we can do for the.
Yeah, no, yes, I do think that's useful.
For the fitness of reconstruction.
And it's graven. It's actually baptized by Brian.
Graven?
Yeah, like the rock.
I thought it'd make it more acceptable to geologists.
Okay.
Even if it's spelled.
Thank you.
Thank you.
I must have.
All right, so we're at about 10 o'clock. If we have any final questions from the audience? No? Is there any more online going? Just two. Okay, great. Let's thank Adriano first. Thank you.